Coronary CT angiography is a non-invasive, cost-effective method providing details on coronary structure surpassing more traditional techniques in terms of cost and time. In our project, using deep learning on CCTA images, particularly convolutional neural networks, we aim to determine whether a point inside or nearby a coronary artery belongs to a coronary ostium. Using CAT08 and ASOK datasets, we assigned ASOK patients to training and validation, while CAT08 for testing. When performing splitting, we ensured that images of the same patient would be found in the same set, given their correlation. To generate the network input, we initially aimed to divide patient volumes into smaller cubes, assigning labels based on proximity to coronary ostia. However, due to computational costs, we opted for a strategy where 50 points were randomly selected from the coronary artery graph, while another 50 were chosen from the ostia. Random translations were applied and cubes were built around these points. For the training set, we added random rotations for augmentation. The result is a balanced dataset with isotropic voxel spacing of 0.5 mm. Huntsville units were clipped and standardized based on cube mean and standard deviation. The subsequent step was to design the convolutional neural network. The reference architecture was taken from the literature, and it consists in a fully convolutional neural network divided into a feature extraction network, composed of a stack of 4 dilated convolutions, and a feature classification and regressor network, composed of convolutions of stride 1. Our models had the goal to minimize inference time while retaining a high performance. Each implementation therefore maintained the stack of 4 dilated convolutions, which allows to grow their receptive field exponentially, while the number of parameters increases linearly. The first model developed was therefore a simple adaptation of the previous one, with a reduced number of filters for each layer and a dense network as the classification head. The evolution of the model was a smaller implementation featuring the channel attention mechanism in between each convolutional layer. This allows to weight each feature map based on the result of a squeeze and excitation block. Results from these models show slightly better performance and faster inference by the second model. To speed up inference, a custom depth-wise separable 3D convolution was implemented. It enhances computational efficiency by splitting the convolution into 2 steps. A depth-wise convolution, processing each channel independently, and a point-wise convolution, combining information across channels. At the same time, we pruned models to remove the least significant parameters. This led to more compact and faster models without suffering from a drop in accuracy. For explainability, we predicted by sampling cubes moving from the ostium node forward. Notably, mispredictions are focused on the ostium region's boundary. This is expected since the volumes at this interface contain information related to the ostium due to their dimensions. Thank you for your attention. Here you can find our contacts and the link to our GitHub.